Far ahead of you, further than any night you have ever known, there is a light going out. Not a violent light, not a sun tearing itself apart, but something quieter than that. A small red ember hanging in a dark so complete that the word dark hardly reaches it. Picture yourself drifting there, held gently in a place so distant in time that the whole history of everything you have ever heard of, every star that ever formed, every world that ever turned, has already happened and finished and faded, and all of it lies behind you like a single warm afternoon remembered from the far side of a long life. In that place there is almost nothing left to see. The great fires have burned down. The galaxies that once wheeled in their bright slow spirals have long since dimmed, and somewhere in that immense stillness a last faint red light trembles, the way an ember trembles in a hearth when the fire is nearly done, giving off a warmth so gentle you would have to lean very close to feel it at all. You do not need to be afraid of this place. That is the first thing to say, softly, before anything else. Because there is a way of telling this story that fills it with dread, and that is not the story we're going to tell tonight. We're going to walk out toward that last light together, slowly, the way you might walk out along a shoreline in the evening as the tide goes down, and we're going to look at what is actually there, and what is actually known, and what remains a genuine and open mystery even to the people who have spent their lives studying it. And what you will find, I think, is that the far future of the universe is not a horror at all. It is one of the most peaceful things that physics has ever described. It is a long, slow settling towards stillness, and there is a strange and quiet beauty in it. The kind of beauty you feel when you watch snow fall in the dark and cover everything and soften every edge until the whole world seems to be holding its breath. So let yourself settle now, wherever you are. Let the day you have just lived begin to loosen its hold. You do not have to follow every thread of what I say tonight, and you do not have to stay awake to the end. This is a long walk, and it is meant to be. If you drift off somewhere along the way, out past the last of the stars, that is exactly as it should be. The story will keep unfolding gently around you, and nothing in it will startle you awake. Here is the question we're going to carry with us, the one small light we will hold in our hands the whole way out into the dark. People sometimes ask whether time itself could ever end. They picture a final moment, a last tick of some great clock, a wall at the end of everything beyond which there is simply nothing more. And it is a natural thing to picture, because everything we know inside our own lives has an ending. The day ends, the year ends, the candle burns down, so it feels only reasonable that the universe too should have a last page. But when you look closely at what the laws of physics actually say, something curious happens to that picture. The wall you were expecting is not there. There is no moment marked as the end. And yet something is undeniably running down. Something is being spent that cannot be refilled, and the direction of that spending points, unmistakably, one way, toward the stillness where we began this walk. So the real question, the one we will turn over and over as we go, is a subtler and gentler thing than it first appears. It is not quite, when will time end? It is closer to this. If everything grows still, if every fire goes out and every motion slows and nothing is left that can change, then has time ended, or has it simply run out of things to measure itself against? Those are not the same, and the difference between them, as we will see, is the difference between a wall and a horizon, between a door slamming shut and a room going quiet. Hold that question loosely. We will come back to it when we have earned the answer. But to walk out toward the end of time, we have to begin with the one thread that runs through all of it, the single thread that gives time its direction in the first place. Because before we can ask how the story ends, we have to understand why it only ever runs one way, why you remember the past and not the future, why the cup falls from the table and shatters, but the shards never leap back up and reassemble themselves into a cup, why the warmth of your tea spreads out into the cool of the room and never gathers itself back. All of these are the same fact, wearing different clothes, and that single fact is the quiet engine underneath everything we're going to see tonight. It has a name, and a law, and a history, and we begin there, with the one rule in all of physics that only ever goes forward. Before we turn back to the beginning, let me tell you a little about how we're even able to speak of such a future at all, because it might seem, at first, like the wildest kind of guesswork, like fortune-telling dressed up in the language of science. It is not. The far future of the universe is not prophecy. It is arithmetic. It is the same physics that lets us predict an eclipse centuries in advance, or calculate where a spacecraft must be aimed to arrive at a planet years later, simply carried forward across much longer spans. We know how stars burn because we can measure them burning. We know how fast they spend their fuel because we can weigh them and read their light. And knowing the rate at which the fire consumes the fuel, and knowing how much fuel there is, we can say, with real confidence, how long the fire will last in exactly the way you could estimate how long a candle will burn by watching how quickly the wax goes down. There is no magic in it. There is only the patient extension of laws we have tested 1,000 times, applied to timescales so long that the answers become strange, but no less trustworthy for being strange. The people who first mapped this territory in careful detail were working within living memory, and they approached it not as mystics but as accountants of energy, tallying up every store of usable energy in the cosmos and working out, one by one, how each would be spent and how long the spending would take. They gave the great eras their names, the age of stars and the age of the remnants, and the long reign of the black holes and the final dark, and they worked out the rough timescales of each, and what they produced reads less like a doomsday prophecy and more like a gentle, immensely patient itinerary, a schedule of stillness, a calendar with dozens of zeros in its dates. We will follow that itinerary tonight, stop by stop, but I wanted you to know before we begin that the ground beneath it is solid. This is where the physics leads when you follow it honestly. It is not a story someone made up to unsettle you. It is the quietest and most rigorous of extrapolations, and its destination is rest. Let me stay here a moment longer, in this opening dark, because it is worth feeling the scale of where we are standing before we turn back to the beginning. The universe as we know it is somewhere near 14 billion years old. That is already a number too large to truly hold. If you tried to count out 14 billion seconds, one every second without ever stopping to sleep or eat, you would be counting for more than 400 years. And 14 billion years is not seconds, it is years, each one of them made of more than 30 million seconds of its own. That is the age of everything, from the first light to this very night. And yet, and this is the thing that should make you go quiet, that entire span, the whole 14 billion years that contains every story ever told, is nothing at all next to the future we are walking toward. It is not the opening chapter of the book of time, it is barely the first word of the first sentence. The eras we will pass through tonight stretch so far beyond it that the age of the universe so far becomes a rounding error, a flicker, a single spark at the very start of a fire that burns. For durations the mind simply cannot fold itself around, and so, the light we began with, that last red ember in the dark, is not a fantasy or a fear. It is where the physics leads when you follow it honestly and patiently all the way out. The people who first followed it there were not trying to frighten anyone. They were doing something much more ordinary and much more human. They were trying to understand why a steam engine could never be perfectly efficient. They were trying to understand why heat flows from the hot thing to the cold thing and never the other way. And from that small, practical, almost humble question, they uncovered the deepest and most unbreakable rule we have ever found about the direction of time. That is where we go now, back to the warm rooms and the working machines of the 19th century, to meet the law that only goes forward. There is a rule in physics that behaves unlike almost any other. Most of the laws you were taught, if you were taught any, run just as happily backward as forward. The planets could orbit the other way and no law would complain. Drop a ball and film it falling, then run the film in reverse, and what you see, the ball rising smoothly into a waiting hand, breaks no rule of motion at all. At the level of individual particles, of single collisions, of the basic equations that govern how one thing pushes on another, time has no built-in direction. The mathematics does not care which way the film runs. This is one of the strangest and least appreciated facts about the deep machinery of reality. Almost everything down at the bottom is reversible, and yet the world you live in is anything but. You have never once seen a shattered cup gather itself back together. You have never seen a puddle climb back into a glass, or smoke pour back into a chimney, or the heat of a warm room flow back into the radiator and leave the air cold. You have never seen an egg unscramble. The world you actually inhabit has a powerful and obvious direction to it, a before and an after that can never be swapped, And this direction is so total, so woven into every single thing you do, that you almost never notice it. The way a fish is said not to notice water. Every memory you have is of the past and never the future. Every plan you make bends toward a future you cannot yet see. The whole shape of a life, of a day, of a single breath drawn in and let out, runs one way only. So here is the puzzle that sits at the very heart of tonight. If the fundamental laws do not care about the direction of time, where does this overwhelming one-way flow come from? Why does the universe you live in have such a strong and unbreakable arrow, when the rules underneath it seem perfectly content to run either way? The answer is one of the great achievements of physics, and it comes down to a single idea, an idea with a slightly forbidding name and a wonderfully simple heart. The name is entropy. And the law that governs it is called the second law of thermodynamics, which is a heavy phrase for something you understand already in your bones, whether or not you have ever heard it named. Let me give you the heart of it first, before any of the machinery. Imagine you have a brand new deck of cards fresh from the box, arranged in perfect order, every suit together, every number in sequence. There is exactly one arrangement that counts as that perfect order, just one. Now, start shuffling. With every shuffle, the cards move toward disorder, and here is the key: they move toward disorder not because there is some force pulling them that way, but simply because there are so many more ways to be disordered than to be ordered. There is only one perfectly sorted arrangement, but there are almost unimaginably many jumbled ones. So when you shuffle, you're overwhelmingly likely to land in one of the countless messy states, and almost never in the single tidy one. You could shuffle a deck every second for the entire age of the universe, and never once, not one single time, shuffle it back into perfect order by chance, not because it is forbidden, only because it is so staggeringly unlikely that never is, for all practical purposes, the honest word. That is entropy. Entropy is, in essence, a measure of how many different ways the tiny hidden pieces of a thing can be rearranged, without changing how it looks from the outside. A tidy, ordered, low-entropy state is one that can be built in very few ways. A jumbled, spread-out, high-entropy state is one that can be built in an enormous number of ways. And the second law of thermodynamics says something almost embarrassingly simple once you see it this way. It says that an isolated system, left to itself, will move from the less likely states toward the more likely ones, from order toward disorder, from few arrangements toward many, simply because the many outnumber the few by margins that dwarf every large number you have ever met. Entropy in an isolated system tends to increase. It does not have to in the sense of an iron prohibition. It simply does, with a reliability so total that in all of human history and all of scientific observation, at the scale of everyday things, it has never once been seen to fail. Think of a drop of cream falling into a cup of dark coffee. At the first instant, it is a tight, distinct swirl, a small ordered island of white in the black, and then, slowly, it unspools. It threads out into ribbons, and the ribbons thin and the thinning ribbons blur, until the whole cup is an even, uniform, quiet brown, and there is no way at all to look at that finished cup and know where the cream first went in. The cream is spread into the coffee because there are so many more ways to be spread out than to be gathered, and once it finds those spread out arrangements, it will never, by any stirring of its own, gather itself back into a drop. You could sit and watch that cup for the entire lifetime of the sun, and it would not happen. The cream does not unmix, the coffee does not sort itself. This is the arrow of time, and you have watched it 1,000 mornings without once thinking of it as the deepest law in physics. Now here is where it becomes beautiful, and where it begins to reach all the way out to that last red ember we started with. The universe as a whole is, as far as we can tell, an isolated system. There is nothing outside it for it to trade with. And so the universe as a whole is doing exactly what the cream does in the coffee, exactly what the shuffled deck does, exactly what the warm tea does as it cools into the room. It is moving steadily and irreversibly from more ordered arrangements toward more disordered ones, from concentrated stores of usable energy toward energy that is spread thin and even and can no longer be put to work. The early universe was, in this precise sense, extraordinarily ordered, a tightly wound spring of concentrated energy. And ever since, that spring has been unwinding. Every star that shines is unwinding it. Every fire, every heartbeat, every thought you have ever had has been paid for by a little more of that spring letting go. The direction of that unwinding is the direction of time itself. The reason you remember yesterday and not tomorrow, the reason the cup shatters and never reassembles, the reason we can walk out toward the end of the universe but never back to its beginning, is that the universe is a great spring slowly releasing its tension, and the release only ever goes one way. And this is the thread we will follow all the way out into the dark, because if the universe is unwinding, if entropy is always climbing, then somewhere far ahead lies a state of maximum entropy, a state so thoroughly spread out and evened over that there is nothing left to unwind, no gradient left to exploit, no difference left between here and there, hot and cold, before and after. That state has an old and slightly melancholy name. It is called the heat death of the universe, and it is the place we are walking toward. But before we can understand what it truly is, and whether that heavy word death is even the right one, we have to understand where this whole idea came from, because it did not arrive fully formed. It was discovered piece by piece by real people in real rooms, wrestling with a problem that had nothing at all to do with the end of time. They were trying to build a better engine, and that is where we go next. It is worth pausing to feel just how deep this idea runs, because the second law is not one law among many, but something closer to a law about laws, a rule that sits underneath and constrains everything else. Physicists sometimes say it with a certain reverence. The great astronomer Arthur Eddington once remarked that if your pet theory of the universe is found to disagree with the second law of thermodynamics, then there is nothing for it but to abandon your theory, because while a great many things in physics can be revised, the second law occupies a kind of supreme position among them. You can imagine a universe with different particles, different forces, different constants, and physicists cheerfully do imagine such universes, but a universe in which entropy spontaneously decreased, in which the cream leapt back out of the coffee and the shattered cup gathered itself whole, is not merely unusual. It is a universe running backward, a film played in reverse, and we have never once in all of history, in any laboratory or any corner of the sky, seen the film run that way. And yet, and here is a subtlety worth holding gently, the second law is not quite like the other laws in one important respect. It is not an absolute prohibition, but an overwhelming probability. There is no iron rule forbidding the cream from Ewan mixing. It is simply that the number of arrangements in which the cream is spread out so vastly, so incomprehensibly outnumbers the number in which it is gathered, that the gathering never happens, not because it cannot, but because the odds against it are so steep that the word never becomes, for all practical purposes, exactly true. This is a different flavour of certainty than most of physics offers. It is the certainty not of a locked door, but of a coin that, flipped enough times, always comes up somewhere near half heads and half tails, never once, in the whole life of the universe, coming up heads 1 trillion times in a row, not because such a run is forbidden, but because it is so absurdly unlikely that it simply does not occur. The arrow of time, in other words, is written not in the fundamental equations, but in the sheer weight of numbers, in the crushing statistical majority of the disordered over the ordered. Time flows one way because there are so many more ways to be later than to be earlier, so many more ways to be spread out than to be gathered. There is one more thread here, and it reaches all the way back to the beginning of everything, so let me pull it gently. If entropy is always increasing, if the universe is always becoming more disordered, then it must once have been more ordered than it is now, and going back and back, it must have begun in a state of extraordinarily low entropy, extraordinarily high order, a tightly wound spring indeed. This is one of the genuine deep puzzles of physics, and I want to name it honestly as the open question it partly is. Why did the universe begin in such a special, such an ordered, such a low entropy state to begin with? That the second law holds is beyond doubt. Why the universe was wound so tightly at the start, so that it has had somewhere to unwind toward ever since, is a question that touches the very origin of time and is not fully answered. We do not entirely know why the beginning was the way it was, but we know with complete confidence the direction it set everything moving, and that direction is the one we are following tonight, out toward the stillness. The low entropy past is a mystery, the high entropy future is a near certainty, and we, and everything we love, live in the brief and precious slope between them, in the fall from order toward disorder, which is the only place, it turns out, where anything interesting can ever happen at all. Rest here for just a moment before we go looking for the people who found this law. Notice how gentle it actually is, this second law. Once you have stripped the fearsome name away from it, it is not a force. It is not pushing anything. It contains no malice and no urgency. It is simply the quiet, statistical truth that spread out things are more common than gathered ones, and that a universe left to wander among its possibilities will wander, overwhelmingly, into the spacious and the even and the calm. There is nothing violent in it. When your tea cools, no battle is being fought. The warmth is simply finding the vastly larger number of ways to be everywhere in the room rather than concentrated in the cup. And the far future we are walking toward is, in the end, only the largest and slowest version of your cooling tea. The whole universe finding at last the most spacious and even arrangement of all. Keep that in mind as we go. Whatever heavy words we meet along the way, the thing itself is soft. The story of how we came to know all this begins not with a philosopher gazing at the stars, but with a young French military engineer thinking about steam. His name was Sadi Carnot, and in the early 1800s he was living in a world being remade by the steam engine. All around him, machines of iron and fire were beginning to pump water from mines, to drive looms and mills, to move great weights that no team of horses could ever have shifted. And yet nobody really understood these machines, not deeply. They had been built by tinkerers and improved by trial and error, by men with a feel for metal and pressure. But the underlying principle, the reason an engine could turn heat into motion at all, remained a kind of fog. Carnot set himself a question that sounds almost too simple to be profound. He asked, what is the greatest amount of useful work you could ever, even in principle, squeeze out of a given flow of heat? He was, without knowing it, standing at the doorway of one of the deepest truths in all of physics. In the year 1824, in a slim book that almost no one read at the time, Carnot laid out an argument of startling elegance. He imagined an idealized engine, a perfect one, with no friction and no waste, and he showed that even this perfect engine, the best that could ever possibly exist, could not turn all of its heat into work. Some fraction always had to be surrendered, passed down from the hot source to a colder sink, simply lost to the cold. There was a ceiling on efficiency that no cleverness, no engineering, no future invention could ever break through. It was not a limitation of the machinery, it was a limitation woven into the nature of heat itself. Carnot had glimpsed in the workings of a steam engine the first shadow of the second law. He died young, in 1832, of cholera, only 36 years old, and because he had died in an epidemic, many of his papers and belongings were burned as a precaution, so that much of what he had thought was simply lost. His little book might have vanished entirely into obscurity, but it did not. A generation later, others picked up the thread, and among them was a German physicist named Rudolf Clausius, a careful and rigorous mind who took Carnot's insight and sharpened it into something exact. It was Clausius who, in the 1850s and 60s, gave the world the clear statement that heat does not spontaneously flow from a colder body to a hotter one. And it was Clausius who, in the year 1865, needed a name for the quantity that measured this one-way flow, this thing that always increased when heat moved and work was done. He reached back into Greek, to a word meaning transformation, and coined a term that would outlast him by far. He called it entropy. He chose the word deliberately to rhyme with energy, because he sensed that the two belonged together, one the great conserved quantity of the universe, the other the great increasing one. Energy is never created or destroyed, only moved and changed. Entropy, Clausius realized, only ever grows. He summed up the whole of thermodynamics in two short and almost poetic clauses. The energy of the universe is constant. The entropy of the universe tends toward a maximum. In that second clause, quietly, without any fanfare, is the entire far future we are walking toward tonight. But there was still something missing, something deep, and it took one more mind to supply it. Clausius could describe entropy, could measure it, could write down how it behaved, but he could not yet say what it truly was. That final step belonged to an Austrian physicist named Ludwig Boltzmann, and it is one of the most beautiful pieces of reasoning in the history of science. Boltzmann asked what heat and entropy really are at the level of the invisible pieces, the countless atoms and molecules jostling and colliding that make up any warm thing. And he arrived at the answer we have already met tonight, the answer of the shuffled deck and the spreading cream. Entropy, Boltzmann showed, is a measure of the number of ways the hidden, microscopic pieces of a system can be arranged while looking the same from the outside. A hot gas has enormously many such arrangements. As it spreads and cools and evens out, it moves toward the states that can be built in the most ways, and those are the states of higher entropy. The second law was not some separate decree laid on top of physics. It was simply what you get when you have vast numbers of particles wandering blindly among their possibilities. It was statistics, raised to the scale of the universe. Boltzmann was so certain of this insight, and so moved by it, that he asked for his equation relating entropy to the number of microscopic arrangements to be carved on his gravestone, and it is there to this day in a cemetery in Vienna, a short and elegant line of mathematics standing over the man who found it. He did not have an easy life. His ideas were fiercely resisted by many of his contemporaries, some of whom did not even believe atoms were real, and the fight wore on him. He struggled with deep bouts of despair, and in the year 1906, while on holiday, he took his own life, not knowing that within just a few years the reality of atoms would be confirmed beyond any doubt and his vision would triumph completely. There is a real sadness in that, a man who could not see how thoroughly he had won. But the idea he gave us is luminous, and it is the idea we carry now. Entropy is the count of the ways. Time runs in the direction of the more numerous ways, and the universe, wandering among its countless possibilities, drifts always toward the states there are the most of, which are the spread out ones, the even ones, the still ones. So now we have the law, and we have the faces of the people who found it, and we have the single thread that gives time its arrow. The universe is unwinding from a tightly ordered beginning toward a spread out end, and every star that shines is a part of that unwinding. Which means, if we want to know how the far future unfolds, the very next thing we have to understand is the stars themselves. Because for now, in this present era, the stars are where the great unwinding is most visibly happening. They are the fires that light the whole story. And to know when the darkness comes, we first have to count the fires and learn how long each kind of fire can burn. There is a detail in Clausius's work that I find quietly moving, and it is worth drawing out because it shows how close these 19th century minds came to seeing the whole far future without quite naming it. When Clausius wrote that the entropy of the universe tends toward a maximum, he understood, at least dimly, what that maximum would mean. It would mean a state in which no further useful work could be extracted from anything, because all the differences that make work possible, the difference between hot and cold, between high and low, between concentrated and spread out, would have been evened away. A German physicist of the same era, Hermann von Helmholtz, drew out this implication and spoke of a coming state in which the universe would be condemned, as he put it, to a condition of eternal rest, a phrase that already carries the whole idea of the heat death within it. These were men doing thermodynamics to understand engines and heat and energy, practical questions of their industrial age, and yet the mathematics they uncovered reached out, almost against their will, to the end of all things. They had found, in the behaviour of steam and heat, the far destiny of the cosmos, and some of them knew it, and some of them found it sobering, and some found it strangely beautiful, and the argument over how to feel about it has never entirely stopped. And Boltzmann, the man who saw most deeply of all, left us one more gift that bears on tonight, a genuinely open question that he was the first to pose clearly. If the universe naturally tends toward disorder, toward the spread out and the even, then how did it ever come to be in the ordered, concentrated state it plainly started from? Why is there any order here at all for us to watch unwinding? Boltzmann wrestled with this and offered various answers, some of which he was not satisfied with. And the truth is that the question he raised remains genuinely open to this day, tangled up with the deepest puzzles about the beginning of the universe and the origin of time's arrow. I flag it as open honestly because it is. We understand the unwinding with great precision. Why the spring was wound in the first place is a mystery that reaches back past all the physics we have followed tonight to the very first instant, and there the confident textbook voice must give way to genuine wonder. Boltzmann saw the shape of the question more than a century ago, and we have not fully answered it yet, and there is something companionable in that, in sharing a live mystery across so many years with the man who first felt its weight. Before we go counting the fires, let me say one quiet thing. and then I will not interrupt the walk again for a while. If you're finding something restful in this, in being told true things gently in the dark, then this small channel is here for exactly that, night after night, and it grows only when someone chooses to follow along. If you would like more of these long walks towards sleep, you are warmly welcome to subscribe, and if that is not for you tonight, that is perfectly fine too, and the story continues either way. There, that is the only time I will ask. Now let us go and look at the stars and learn how long a fire can burn. Look up on a clear dark night far from any town and the sky is scattered with fires. Thousands of them are visible to the naked eye, and behind those, uncountable more, until the faint milky band across the sky resolves, in a good telescope, into the massed light of hundreds of billions of stars, all of them part of our own single galaxy, and our galaxy itself only one among a comparable number of galaxies spread through the observable universe. The numbers here climb so quickly that they stop meaning anything, so let me try to give them a shape you can hold. If you took every grain of sand on every beach and in every desert on the whole of the Earth and counted them, you would arrive at a number, a huge one. The number of stars in the observable universe is thought to be considerably larger than that. There are more suns out there than there are grains of sand down here. That is the inventory of fires we are working with, and every one of them is burning, and every one of them, in burning, is spending fuel that will not be replaced. Because that is the thing about a star. It is not eternal. It looks eternal to us, fixed and changeless across a human lifetime. The same constellations our distant ancestors saw, the same North Star to steer by. But this steadiness is an illusion born of our own brief lives. A star is a fire, and like any fire it has a beginning, a long burning middle, and an end when the fuel runs low. The only reason the stars seem changeless is that their fires are so enormous and so slow that a human life, even the whole span of human history, is far too short to watch one burn down. But burn down they do, and the length of time a given star can shine depends more than anything else on one thing, its mass, on how much of it there is. And here the universe hands us a beautiful and slightly counterintuitive rule, one worth pausing over. You might expect that the biggest stars, the ones with the most fuel, would burn the longest. It seems only fair. A bigger woodpile should make a longer fire, but stars do not work that way, and the reason is one of the loveliest facts in astronomy. The most massive stars, the great blue-white giants, do have far more fuel, but they burn it with such furious, extravagant speed that they exhaust themselves almost recklessly fast. A star born with, say, 20 or 30 times the mass of our Sun may blaze through its entire life in just a few million years, a mere eye blink on the cosmic scale, before it dies in a spectacular explosion. It is a candle held to both ends of a bonfire, dazzling and brief. Meanwhile, the smallest stars, the dim red dwarfs with only a fraction of the Sun's mass, are so miserly with their fuel, so slow and cool and gentle in their burning, that they can keep going not for millions of years, not for billions, but for many trillions of years. The smallest, faintest, least impressive stars in the whole sky are the ones that will outlast everything else by an almost incomprehensible margin. In the great fire of the cosmos, it is not the roaring flames that endure, it is the quiet, patient embers. Our own Sun sits somewhere comfortably in the middle of this range. It is not a giant and not a dwarf, a steady, ordinary, middle-sized star, and its middle-sized nature gives it a middle-sized life. The Sun has been shining for about 4.5 billion years already, and the physics of how it burns tells us it has roughly another 5 billion years of steady, shining left before it begins to change in earnest. 5 billion years. Set that against a human life of perhaps 80 years, and it is so vast a span as to be meaningless. And yet, and here is where we must begin to stretch our sense of time, 5 billion years is short. It is short. Against the far future we are walking toward tonight, the entire remaining life of the Sun is a small early scene, one of the first we will pass, and we have an immense distance still to travel beyond it. Let me try to lay out the ladder of these times, because the whole shape of the far future is really just this ladder climbed rung by rung, each rung a factor of 10 or more beyond the last. The most massive stars live only millions of years. Stars like the Sun live for something on the order of 10 billion years all told. Smaller orange stars live for tens of billions. And the smallest red dwarfs, the true long-distance runners, may shine for something like 10 trillion years, which is close to 1,000 times the entire current age of the universe. Sit with that for a moment. There are stars burning in the sky tonight that have barely begun their lives, that will still be glowing faintly long after our sun is gone, long after our galaxy has been transformed, stars whose fires will not gutter out until the universe is nearly 1,000 times older than it is right now. And even those, in the end, will fade. To picture how these times stack up, imagine the whole current age of the universe, all 14 billion years of it, compressed down into a single day, from midnight to midnight. On that scale, all of recorded human history, every empire and every book and every remembered name, occupies far less than the final second before midnight. The sun formed only in the mid-afternoon of that day, and will not exhaust its fuel until well into the following day. But the red dwarfs, the patient ones, are burning on a calendar where our single compressed day is not even the beginning. Their fires last for the equivalent of years of such days stacked end to end. We are, all of us, every star we can see and every world we know, living in the very early morning of the universe, in the freshness of the first light. And it does not feel that way only because a morning that lasts for trillions of years feels, to a creature who lives for 80 of them, exactly like forever. So the stars are spending themselves, each at its own pace, the giants fast and the dwarfs slow, and the great question of the far future's first long era is simply this. When does the last fire go out? When does the final star exhaust the final scrap of its fuel and dim toward darkness, leaving the sky, for the first time in the history of the universe, without a single shining sun anywhere in it? To answer that, we cannot just count the stars. We have to understand what is actually happening inside them, in the crushing heat of their hidden cores, where the fuel is burned. We have to understand how a star holds itself together at all and why, one day, it cannot. And that means going inside. Let me linger a little longer on how these lifetimes are actually reckoned, because it is one thing to be told that a small star lives longer than a large one, and quite another to see why the physics forces it to be so, and the seeing is the soothing part. The key is that a star must produce enough energy in its core to hold up its own weight, and a more massive star weighs vastly more, and so presses down on its core vastly harder. To resist that greater pressure, the core of a massive star must burn far hotter and far faster, fusing its fuel at a furious rate to generate the enormous outward push required. The relationship is startlingly steep. A star 10 times the mass of the sun does not burn 10 times faster. It burns thousands of times faster, because the rate of fusion climbs so sharply with the temperature and pressure of the core. So even though the massive star started with 10 times more fuel, it consumes that fuel thousands of times more quickly, and the arithmetic is merciless. More fuel, burned enormously faster, adds up to a far shorter life. The giants are prodigal. They inherit vast fortunes of fuel and spend them in a wild, brief blaze. The dwarfs inherit little and husband it across the ages. It is the oldest story told in starlight. We can watch this story written across the sky right now, and reading it is one of the quiet triumphs of astronomy. If you gather a great cluster of stars all born together at roughly the same time from the same cloud of gas, and you sort them by brightness and colour, you find that the cluster tells you its own age. In a young cluster, the brilliant blue giants are still shining because not enough time has passed for them to die. In an older cluster, those giants are gone, burned out long ago, and only the cooler, longer-lived stars remain. By noting exactly which stars have died and which still shine, astronomers can read the age of a cluster, the way you might guess the hour of a long party by noticing which candles have guttered out. This is not guesswork. It is a precise and well-tested technique, and it lets us date the oldest star clusters in our galaxy to many billions of years, a beautiful confirmation that the physics of stellar lifetimes we have worked out is genuinely correct. The sky keeps its own clocks, and we have learned to read them. And there is a further wrinkle, a lovely one, that reaches forward into the far future. When astronomers first counted up the stars and worked out how long the age of starlight would last, they were counting mostly the stars they could easily see. But the galaxy is not done making stars, not yet. There is still gas drifting between the stars, the raw material from which new suns condense, and for a long time to come, new stars will keep being born even as old ones die. The age of starlight is not simply the lifetime of the stars that exist now. It is the whole long era during which stars of any kind still shine, including all the generations yet to be born from the gas that remains. Only when that gas is finally exhausted, when the last cloud has collapsed into the last new stars and even the slowest of those has burned down, does the great bright era truly close. And that is why the number reaches out to something like 100 trillion years, far beyond the life of any single star, because it must wait for the very last of the very last, the final dim red dwarf born from the final scrap of gas, to finish its long, slow burning. The lights go out not all at once but gradually, over an immensity of time, the sky dimming so slowly that any creature living through it would never notice the change across 1,000 generations, until at last the final ember cools, and the great age of starlight, the age we happen to live in, quietly ends. A star is, at heart, a balancing act of staggering scale, a truce between two titanic forces that would each, on their own, destroy it. Understanding that truce is the key to understanding not only how stars live but how and when they must die. And so it is worth going slowly here, into the deep interior of a sun, to see what actually holds a fire together across billions of years. The first of the two forces is gravity, and gravity for a star is relentless and inward. A star is an enormous quantity of gas, mostly hydrogen, the simplest and lightest element, gathered into a ball so massive that its own gravity pulls with crushing force toward the centre. If gravity had its way, and nothing opposed it, the whole star would collapse, falling inward on itself, every part of it crushing down toward the middle. Left alone, gravity wants to squeeze a star into a point. Something must be pushing back, hard, every instant, to keep the star from imploding. And something is. That something is pressure, the outward push of hot gas, and the heat that creates that pressure comes from the very centre of the star, from a process that is one of the true wonders of the physical world. In the core of a star, gravity has squeezed the hydrogen so tightly and heated it so ferociously, to temperatures of many millions of degrees, that the hydrogen nuclei, which normally repel one another fiercely, are slammed together hard enough to fuse. 4 nuclei of hydrogen, through a chain of steps, combine to make one nucleus of helium, the next element up. And here is the alchemy at the heart of it. The helium that comes out weighs just a little less than the 4 hydrogen nuclei that went in. A tiny sliver of mass has vanished. But mass, as Einstein showed us in that famous relation between mass and energy, is not really gone. It has been converted into pure energy, released as a flood of light and heat pouring outward from the core. That released energy is the fire of the star. It is the outward pressure that holds gravity at bay. It is the light that reaches across the darkness to warm a planet and let a night sky exist to be looked at. So a living star is a balance, moment by moment, between gravity pulling in and the pressure of fusion pushing out. Physicists call this balance hydrostatic equilibrium, a heavy phrase for a delicate and beautiful thing. Picture a great stone balanced perfectly on a slope, held in place not by being wedged, but by a constant active push from below that exactly matches the pull of its weight. As long as the fusion in the core keeps burning, the push holds, and the star shines steady and unchanging for billions of years, that reassuring constancy we mistake for permanence. The sun has held this balance for 4.5 billion years, and it will hold it for billions more, but the balance depends entirely on fuel. And the fuel is finite. Here is what will happen when the sun's fuel runs low, and it is worth telling because it is the fate, in one form or another, of countless stars, and because it shows us the machinery of a star's end. When the hydrogen in the core is largely used up, the outward push falters. Gravity, which never rests, presses inward again, and the core contracts and heats further until it grows hot enough to begin fusing the helium ash left behind into heavier elements still, carbon and oxygen. Meanwhile, the outer layers of the star swell enormously, ballooning outward as the star becomes a red giant, so vast that when the sun does this it will likely swell beyond the orbit of the innermost planets. But this is a late, brief, unstable chapter compared to the long, steady burning that came before. A star can only keep climbing to heavier and heavier fuels for so long, and the smaller stars like the sun cannot climb far at all. When it can fuse no further, the sun will shed its bloated outer layers gently into space, a soft glowing shell drifting outward, and leave behind only its exhausted core, a small, incredibly dense, slowly cooling ember about the size of the Earth, but containing much of the mass of a star. That ember is called a white dwarf, and we will meet it again, because in the far future white dwarfs are among the last things left. Now, you might reasonably ask how we could possibly know any of this. We cannot cut a star open. We cannot send a probe into that crushing, blazing interior where no instrument could survive for even an instant. The centre of the sun is utterly hidden from us, buried beneath hundreds of thousands of kilometres of blinding plasma, and yet we speak of its temperature, its pressure, its fusion, with real confidence. How? The answer is one of the quiet triumphs of science, and there is something deeply soothing in it, in the sheer ingenuity of how we come to know things we can never see. We know the interiors of stars through several remarkable windows. One is simply physics and mathematics. Knowing a star's mass, its size, and the light it gives off, and knowing the laws of gas and gravity and nuclear physics that we have tested exhaustively here on Earth, we can calculate what must be happening inside to produce exactly the star we observe. The equations are demanding, but they are not mysterious, and they yield the temperatures and pressures of the core with real precision. But there are also direct messengers from inside the fire. Stars ring very softly like bells. Their surfaces pulse and quiver with waves that travel down through their interiors and back up, and by watching those quivers with exquisitely sensitive instruments, in a field called astroseismology, we can read the internal structure of a star the way a geologist reads the inside of the Earth from the echoes of earthquakes. And there is one messenger more astonishing still. The fusion in the sun's core produces not only light, but ghostly particles called neutrinos, which barely interact with anything at all, and so stream straight out of the sun's centre and across space, passing through the entire body of the sun and the Earth, and you, almost as if none of it were there. Trillions of them are passing through your body this very second, from the core of the sun, having left it only minutes ago. Physicists have built enormous detectors, deep underground to shield them from all other disturbances, vast tanks of water or special fluids watched by banks of sensitive eyes, patient enough to catch the rare neutrino that does interact. And when we count those neutrinos, they tell us the rate of fusion in the sun's heart right now. We have, in a real sense, taken the pulse of the sun's core directly, using particles that flew straight out of the fire. That is how we know, not by guessing, but by listening, with enormous care, to the faint messages the star itself sends out. And so we can say, with genuine confidence, how stars live and how they die, and how long their fires can last. Which brings us back to our ladder of time, and to the most important rung on it for the far future, the dimmest and most patient stars of all. Because the giants die fast and the sun dies in its billions of years, but it is the smallest red dwarfs, burning so slowly and so long that truly set the length of the age of starlight. And there is a story about those stars, a story of a confidently held wrong idea that had to be corrected, that shows us just how much longer the light will last than we once believed. There is one more window into the hidden hearts of stars that I did not mention, and it is perhaps the most astonishing of all, because it turns the whole business of a star's death into something we can actually measure and confirm. When a massive star finally collapses and explodes as a supernova, the fusion that powered it does not simply stop. In the fury of the collapse and the blast, in temperatures and pressures far beyond anything a living star ever reaches, brand new elements are forged, heavier ones forged in seconds in the explosion itself. And this is not a story we merely tell, we can watch it happen. When a nearby star exploded in the sky in the late 1980s, close enough to study in detail, our detectors on Earth caught a burst of those ghostly neutrinos arriving from it. Particles flung out from the collapsing core in the very instant of its death, having crossed a vast gulf of space to reach us. We caught the death cry of a star, written in neutrinos, and it matched, in its timing and its character, exactly what the physics of stellar collapse had predicted. That is how deeply we understand these fires. We have not only worked out how stars live and die in theory, we have caught the particles thrown off in the very moment of a star's death and read in them the confirmation of our understanding. When we speak, then, of how the stars will end, and how long their fires will last, we are not guessing. We are extending out into the deep future, a physics we have tested against the living and dying stars themselves and found true. And there is a gentle symmetry worth noticing here, one that ties the whole arc of tonight together. The heavy elements forged in those stellar deaths, the carbon and oxygen and iron scattered out into space by exploding stars, are the very stuff that later gathers into new stars, new worlds, and eventually into living things. The atoms that make up your body were assembled in the cores, and the death throes of stars that lived and died before the sun was born. You are, quite literally, made of the material that the great unwinding of the universe cooked up along the way, gathered for a little while into the warm arrangement that is you. And so the same process that will one day dim the last star is the process that made you possible in the first place. The dying of the stars and the living of everything that ever lived are not two stories but one, and we are, each of us, a brief, bright chapter written in the ash of older fires. Hold that thought gently as we go on, because it will meet us again, softened and completed, at the very end of our walk. For a long time, when astronomers thought about how long the era of stars would last, they thought mostly about stars like the Sun and about the giants, because those are the stars that are easy to see and easy to study. The red dwarfs, the small cool ones, are so dim that even the nearest of them cannot be seen with the naked eye, despite being, we now know, by far the most common kind of star in the whole galaxy. The great majority of the stars in existence are these small, faint, overlooked embers, and there was a natural assumption, an intuitive one, about how they would age. Astronomers reasoned by analogy with the sun. A sun-like star burns the hydrogen in its core, and when that core hydrogen is exhausted, the star begins to die, even though most of its total hydrogen, out in the unburned outer layers, has never been touched at all. A star like the sun uses only a small fraction of its total fuel, because it has no way to bring the fresh hydrogen from its outer regions down into the burning core. The good fuel in the outer layers is simply stranded, unusable, wasted, while the core burns out. So it was assumed, reasonably enough, that red dwarfs would work the same way, burning only their core fuel and then dying with most of their hydrogen still stranded and unspent. If that were true, the red dwarfs would live a long time, yes, but not the almost unimaginably long time we now believe. The correction, when it came, revealed something wonderful about these little stars, and it came not from a new telescope but from careful theoretical modelling of how heat and matter move inside a small star. Work carried forward significantly by the astrophysicists Fred Adams and Gregory Laughlin, among others, who in the late 20th century mapped out the far future of the cosmos in careful detail. Here is what the models revealed. A red dwarf is so small and so thoroughly churned inside, fully convective, meaning its material circulates from surface to centre and back like a slowly boiling pot, that it does not strand its fuel the way the sun does. The whole star is stirred together continuously, so that fresh hydrogen from the outer regions is carried down into the core and the burnt helium is carried up and out, and the star gets to use very nearly all of its fuel, not just the small central fraction. A red dwarf is not a wasteful burner like the sun. It is a supremely efficient one, sipping its fuel slowly and using nearly every drop. And because it is both efficient and slow, its life is extended to a length that dwarfs even the generous estimates that came before. The smallest red dwarfs, we now think, can go on shining for something on the order of 10 trillion years, and by some estimates even longer, an interval so vast that our sun's whole life, and the whole history of the universe so far, disappears into insignificance beside it. There is a gentle lesson tucked inside this correction, and it is very much in the spirit of tonight. The stars that will endure the longest, that will still be quietly glowing when everything grand and bright has long since gone, are the small ones, the humble ones. The ones too faint to have a name in any old story or a place in any constellation. The blazing giants that dominate our images of space are gone in a cosmic instant. The patient little embers outlast them all by a factor of millions. If there is a kind of quiet consolation in the physics of the far future, some of it is here, in the fact that gentleness and patience in the world of stars are precisely what endures. Let me set a small image beside these numbers to hold them steady. Think of the difference between a candle and a smouldering coal of peat. The candle gives a bright, clear, cheerful flame, but it is gone in an evening. The peat coal barely seems to burn at all, just a dull red glow and a thread of smoke, and yet a well-banked peat fire can smoulder on through a whole long winter's night and still be warm in the morning, when the candles are all long since guttered and cold. Our sun is the candle, bright and warm and finite. The red dwarfs are the banked coals, dim and slow and almost endless, still faintly glowing in the deep cold morning of a universe grown old. And so the true end of the age of starlight is set not by the bright stars but by these dim ones, and it comes, very roughly, somewhere around 100 trillion years from now, when the last and slowest of the red dwarfs finally exhausts its fuel and cools toward darkness. 100 trillion years. Try gently to feel the size of that. The universe is 14 billion years old. 100 trillion is more than 7,000 times that. If you compressed the entire life of the universe so far down into a single hour, the age of starlight would not end for something like 7,000 more hours beyond it, which is the better part of a year of such hours. We are living right now in the very first hour. Every star you have ever seen or heard of, our sun and all its neighbours, every star in every photograph ever taken, belongs to this brief, bright opening hour of a story that runs on for the equivalent of a year and more of such hours into the dark. We are creatures of the first light, and we mistake the first light for all the light there is. But 100 trillion years does pass in the end, however vast it seems. The slow coals do burn down, and there comes a time when the last star flickers and fades, and for the first time since the universe was very young, the sky holds no shining sun anywhere. The great age of starlight is over, and yet, and this is the thing we must sit with, the universe is not empty then, and it is not truly dark, and it is very far from finished, because when the stars die, they leave things behind. Dense, strange, long-lived remnants, still faintly glowing with stored heat, drifting through a galaxy gone dim. And those remnants have a long, long era of their own still to come. We have passed the age of stars, now we walk into the age of the embers they left behind. It is worth sitting with the sheer strangeness of the red dwarf's patience, because there is a lovely piece of physics in why these small stars burn so slowly, and it comes back once again to that balance between gravity and pressure we spoke of. A red dwarf has so little mass that its core is under comparatively gentle pressure, nothing like the crushing weight at the heart of a larger star, and because the core is under less pressure, it is cooler, and because it is cooler, fusion proceeds at a far more leisurely pace, sipping the hydrogen rather than gulping it. A gentle core makes a slow fire, and a slow fire, tended by a star that also happens to circulate its whole supply of fuel down into that core to be used, can last almost unimaginably long. The very qualities that make a red dwarf unimpressive to look at, its coolness, its faintness, its small mass, are precisely the qualities that grant it its immense longevity. It is the meek inheriting the cosmos in the most literal way physics allows. And there is a further consequence, one that is genuinely poignant and worth naming, about what the red dwarf era will actually look like. Long after our sun is gone, long after the bright familiar stars have all died, the galaxy will still be scattered with these dim red points, burning on and on. Any world orbiting such a star would sit in a deep red light, a perpetual dim sunset, warmed gently by a fire that would still be burning long after every star we can see tonight has become a cold cinder. There is a whole immense chapter of cosmic time, stretching from where we are now out to that 100 trillion year mark, that belongs almost entirely to these small red stars, a long slow red evening of the universe, quiet and dim and enduring, that we, living in the bright morning, will never see. We happen to have arrived early, in the age of blue and white and yellow fire in the loud, bright opening of the story. The long red evening comes after, patient and gentle, and it lasts far longer than the morning we call the whole of history. Let yourself drift here for a breath at the close of the age of starlight. There is no need to hold every number in your mind. Let them go soft, the way the last stars go soft. What matters is only the shape of the thing, the way one long era of the universe gives quietly onto the next, each far longer than the one before, each darker and calmer, like the deepening hours of a very long night. You have already walked with me past the death of the sun, and out beyond the last of the little red coals, into a dark no living eye has ever seen. And still we are near the beginning. Rest, and we will go on. When the last star has died, the universe enters a long twilight that physicists sometimes call the degenerate era, a strange and lovely name for the age of stellar remnants. To understand it, we have to meet the things that stars leave behind when their fires go out, because the sky of the far future, though it holds no true stars, is not entirely without light. It is scattered with the cooling corpses of stars, and some of them glow, faintly and for an astonishingly long time, on stored warmth alone. There are three main kinds of remnant, and which one a star becomes depends on how massive it was in life. The most common, the fate of stars like our Sun, and of all the smaller stars, is the white dwarf we met earlier, that exhausted core left behind when a modest star sheds its outer layers. A white dwarf is a remarkable object. It packs something close to the mass of the Sun into a ball roughly the size of the Earth, which means its material is crushed to a density almost impossible to picture. A single spoonful of white dwarf matter would weigh as much as a small mountain. What holds such an object up, now that its fire is out and fusion no longer pushes back against gravity, is not heat at all, but a subtle quantum effect, a rule that forbids the crushed electrons from being squeezed into exactly the same state, and this quantum stiffness alone props the whole star against its own crushing weight. A white dwarf is born blazing hot at tens of thousands of degrees, glowing white from the leftover heat of the star that made it. But its fire is out. It generates no new energy. And so, across the ages, it simply radiates that stored heat away into space and slowly cools from white to yellow to red, and finally, after an almost inconceivable span of time, to a cold, dark, dead cinder, a so-called black dwarf, no longer glowing at all. And here is a quiet fact worth holding. The universe is not yet old enough for a single black dwarf to exist. Not one. Every white dwarf ever formed is still faintly warm, still glowing, because the time it takes to cool completely is far, far longer than the entire age of the universe so far. The first truly cold, dark black dwarf will not appear for an amount of time so long that the present age of everything is, beside it, negligible. The more massive stars leave behind stranger remnants still. A star considerably heavier than the Sun ends its life not gently, but in a colossal explosion, a supernova, one of the most violent events in nature, in which the core collapses catastrophically and the outer layers are blasted into space, briefly outshining an entire galaxy. What is left behind is a neutron star, an object even more extreme than a white dwarf. Here gravity has won a further round, crushing the electrons and protons of the core together into neutrons, packing something more than the mass of the Sun into a ball only about the size of a city, perhaps 20 kilometers across. The density is beyond imagining. A sugar cube of neutron star material would weigh about as much as all of humanity put together, every living person compressed into that single cube. Neutron stars spin, often astonishingly fast, some hundreds of times a second, and they too, over vast ages, will cool and slow and grow quiet, joining the slow parade of dark remnants drifting through the dead galaxies. And the very most massive stars leave behind the strangest thing of all, an object so extreme that gravity has overwhelmed every force that might resist it, and crushed the remnant down past all limits into a black hole, a region where gravity is so intense that not even light can escape. We will give the black holes their own long chapter soon, because in the far future they are the last great structures standing, but for now simply note that they are there too, scattered among the white dwarfs and the neutron stars, dark and patient and enduring. So the degenerate era is a sky of embers, cooling white dwarfs, drifting neutron stars, silent black holes, all of them wheeling slowly through galaxies that have gone dark, held together still by gravity but no longer lit by any fire. And this era is long, breathtakingly long, longer by far than the age of starlight that preceded it. If the age of stars runs to something like 100 trillion years, the degenerate era runs to numbers with dozens of zeros after them. Timescales so vast that our usual way of writing numbers becomes useless, and we have to resort to powers of 10 just to speak of them at all. Let me try to give these powers of 10 a human face, because they are about to become the only way we can talk at all, and a number with 30 zeros is meaningless unless we can somehow feel it. Think again of grains of sand. A large handful of sand holds perhaps 10,000 grains. All the sand on a long beach might be a number with somewhere around 16 or 18 zeros. All the sand on every beach and desert on Earth, that number we met earlier, larger than the count of the stars, has perhaps 20 or 21 zeros. And now the degenerate era asks us to think about spans of years with 30, 40, even more zeros, numbers so much larger than all the sand on Earth that the comparison collapses entirely, because a number with 40 zeros is not a little bigger than a number with 20 zeros. It is that number multiplied by itself, a beach of beaches, a world of worlds of grains. When physicists write the lifetime of this era, they do not write it out. They cannot. They write it as 10 raised to some power, and each step up in that power is another factor of 10, another full multiplication of everything that came before. This is the arithmetic of the far future, and it is the arithmetic of patience beyond any patience a living thing could hold. Across such spans, even the seemingly permanent begins to change. The dead galaxies slowly come apart, their remnants flung out into the growing dark or spiralling down toward the great black holes at their centres. The cooling cinders scatter, and there is a question that begins to press on us here, a question that the age of stars never had to ask, because in the degenerate era time grows so long that even the most stable things we know of may not be truly forever. We have been assuming all along that matter itself simply lasts, that an atom, left utterly alone in the dark for ages, remains an atom. But does it? Is matter truly permanent, or does even it, given enough time, quietly come undone? That is one of the great open questions of the far future, and it is where we turn next, gently, into genuinely uncertain ground. I want to dwell on the white dwarfs a little longer, because they are, in a sense, the true inhabitants of the degenerate era, the most numerous of the remnants, since the great majority of all stars, including our own Sun, end as white dwarfs rather than as anything more dramatic. And the physics that holds a white dwarf up is genuinely strange and worth understanding, because it is the first place in tonight's story where the quantum rules of the very small step up to hold up something the size of a world. When a star's fire goes out, there is nothing left to generate the heat and pressure that once resisted gravity, and you might think the exhausted core would simply keep collapsing forever. But it does not. It is stopped by a quantum rule of astonishing subtlety, a principle discovered in the 1920s which says that the electrons in the crushed matter cannot all be squeezed into the same state at once. As gravity tries to pack them tighter and tighter, they resist, not because they repel one another in the ordinary way, but because this deep quantum rule forbids them from occupying the same condition, and so they push back with a pressure that has nothing to do with heat at all, a pressure that would persist even at absolute zero. This quantum stiffness alone holds up the white dwarf, propping a star's worth of mass against its own gravity by nothing more than the refusal of electrons to be identical. There is a limit to how much even this quantum pressure can bear, a famous threshold worked out by a young physicist on a long-sea voyage from India to England in the early 1930s, Subrahmanyan Chandrasekhar, who calculated that a white dwarf cannot exceed about 1 4/10 times the mass of the Sun, before even the electron's refusal fails and gravity wins. Below that limit, the white dwarf endures. Above it, the collapse continues to something denser still. When Chandrasekhar first presented this result, it was fiercely and publicly disputed by one of the most eminent astronomers of the age, who found the implication distasteful and said so cuttingly. And the young man's correct insight was for a time pushed aside by the sheer authority of his senior. But he was right, and the limit bears his name to this day, and decades later he received the Nobel Prize for the work. There is that pattern again, the young mind seeing truly, the established authority resisting, and the truth outlasting the resistance, as it always, in the end, does. Below Chandrasekhar's limit, then, the white dwarf simply persists and cools, and the cooling is the slowest imaginable process. A newborn white dwarf glows white-hot, radiating away the leftover warmth of the star that made it, but it makes no new heat, and so it can only fade, dimming across billions and then trillions of years, from white to yellow to red to a deep dull glow, and at last, after a span of time far longer than the present age of the universe, to a cold black cinder. I mentioned before that not a single black dwarf yet exists, that the universe is simply too young to have cooled even one white dwarf all the way to darkness, and I want you to feel how remarkable that is. Every white dwarf that has ever formed in the entire history of the cosmos is still warm, still faintly glowing, still radiating the ancient heat of its dead parent star. The first fully cold black dwarf lies so far in the future that we live, even now, in the age before the first one, in the freshness before the first of the remnants has even finished cooling. We are that early, we are that near the beginning. Here we step, for the first time tonight, off the firm ground of settled science and out onto ground that is genuinely uncertain, and I want to mark that step clearly, because on this channel, the difference between what we know and what we merely suspect is not a detail to be glossed over. It is part of the calm. There is a real peace in being told, honestly, this part we understand, and this part we do not, and here is exactly where the boundary lies. So let me say it plainly, everything we have walked through so far, the second law, the lives of stars, the remnants they leave behind, is established, tested, textbook physics, as reliable as anything in science. What we are about to consider is not. It is a genuine open question, one that physicists themselves have not settled, and we are going to hold it as the open question it is. The question is whether the proton lasts forever. The proton is one of the basic building blocks of matter, one of the particles that sits in the nucleus of every atom, in every atom of your body, every atom of the Earth, every atom in every star and remnant we have spoken of. Ordinary matter is built from protons and neutrons and electrons, and of these the proton has always seemed the very picture of permanence. As far as anyone has ever observed, a proton simply persists. It does not decay, it does not fall apart. Left to itself, it appears to endure without change. And for most of the history of physics, it was simply assumed that the proton was perfectly stable, eternal, a true and final permanence at the base of the material world. But certain theories that attempt to unify the forces of nature, ambitious ideas that try to show that the different forces we see were once a single force in the earliest instance of the universe, make a startling prediction. They suggest that the proton might not be perfectly stable after all, that very rarely, unimaginably rarely, a proton might spontaneously decay, coming apart into lighter particles and radiation, ceasing to be a proton at all. If this were true, then matter itself would have a finite lifetime. Every atom, given enough time, would eventually dissolve. The white dwarfs and neutron stars and cold planets drifting through the dark would slowly, atom by atom, evaporate away into a thin haze of light and lighter particles until no ordinary matter remained anywhere at all. How rare would this decay be if it happens? Extraordinarily, almost inconceivably rare. Experiments have searched for it, and this is one of the loveliest things about how science handles such questions, because you cannot watch a single proton for the ages it would take to see it decay. Instead, you do something clever. You gather an enormous number of protons together, vast tanks of ultra-pure water deep underground, containing more protons than there are stars in many galaxies, and you watch them all at once, patiently, for years, with sensitive detectors ringing the tank, waiting for even a single one of that immense multitude to come apart. If protons decayed even a little bit often, then among so many of them, some would decay while you watched. And the result of these long patient vigils in detectors such as the great one in Japan, sometimes called Super Kamiokande, is that no clear proton decay has ever been seen, which does not prove that protons never decay. It only tells us that if they do, the typical lifetime of a proton must be longer than something like 10,000 trillion years, a number with more than 30 zeros, far longer than the present age of the universe. So long that even in the vast degenerate era only a tiny fraction of protons would have decayed. So we do not know. That is the honest answer, and it is a genuinely comfortable one to rest in. Either the proton is truly stable, in which case matter endures in some form deep into the far future, cold and dark but persistent, or the proton very slowly decays, in which case across spans of time with those dozens of zeros, all ordinary matter gently dissolves, the cinders of the stars quietly evaporating into a thinning mist of radiation and stray light particles until the material universe as we know it has simply melted away. Both of these are pictures that serious physicists hold as live possibilities. Neither is established, and what is rather beautiful is that in either case the far future grows only more still, more spread out, more even, exactly as the second law promised at the very beginning. Whether matter dissolves or merely cools, entropy keeps climbing, and the universe keeps settling toward its quiet. I find something genuinely soothing in this, and I hope you might too. We have reached a frontier of real human knowledge, a place where the experts themselves say, "We're not sure," and rather than that being frightening, it is somehow restful. The universe does not owe us certainty about its most distant future. It is enough, and more than enough, to have walked this far, to have seen the shape of the possibilities, and to be able to say, with an easy conscience, that here the map runs out and honest wonder begins. This is where the settled science of tonight quietly hands off to open mystery, and there is no shame in the handoff, only a kind of clean, cool honesty, like the moment on a walk when the paved path ends and the soft grass begins. Whatever the ultimate fate of ordinary matter, though, there is one kind of object we have set aside that has a longer story than any star or planet or cinder, an object whose reign in the far future is so long that it defines an entire era all its own. When the stars are gone, and the remnants are cooling, and matter is perhaps slowly dissolving, the great black holes remain, and they remain for spans of time that make even the degenerate era look brief. So we turn now to the black holes, and to the astonishing discovery that even they, the darkest and most permanent seeming things in all the universe, are not forever. Let me say a little more about how those enormous underground detectors actually work, because the method is so patient and so ingenious that it is soothing just to contemplate. Deep beneath a mountain, shielded by more than a kilometre of rock from the constant rain of cosmic particles that showers the surface, sits an enormous tank holding tens of thousands of tons of the purest water ever made, so pure it would be undrinkable, stripped of every trace of contamination that might produce a false signal. The walls of this vast chamber are lined with thousands upon thousands of exquisitely sensitive light detectors, patient electronic eyes staring inward into the dark water, waiting. If a single proton, among the unimaginable multitude in all that water, were to decay, it would produce a characteristic flash of light, a faint blue cone spreading through the water, and those thousands of eyes would catch it and record its signature. And so, for years and years, scientists watch, in shifts, in silence, tending this great still pool buried in the rock, waiting for a flash that so far has never come. There is something almost monastic about it, this long patient vigil kept in the deep dark for an event that may take longer than the age of the universe to occur. And the not seeing is itself a measurement. Every year that passes without a flash pushes the possible lifetime of the proton longer, tells us that if matter decays at all, it does so even more rarely than we already thought. I find a real tenderness in this, in the image of these patient watchers and their still deep pool, and in what their patience has taught us. Because what they have found so far is that matter is at the very least astonishingly durable, stable beyond any span we could ever test directly, and possibly, for all we can tell, perfectly eternal. The building blocks of you, the protons in every atom of your body, have persisted since the first minutes of the universe, nearly 14 billion years, without change, and they may persist, unchanged, for spans so long that the whole history of the stars is a passing moment beside them. Whether they last forever, or only very nearly forever, is a question we cannot yet close, and I am content to leave it open, because either answer is a kind of marvel. To be made of something that old and that enduring, and to be able, for a brief bright while, to arrange it into a mind that wonders how long it will last, is a strange and lovely privilege, and the not knowing does nothing to diminish it. For most of the 20th century, a black hole was understood to be the very definition of permanence and finality. It is a region where so much mass has collapsed into so small a space that gravity becomes overwhelming, curving the fabric of space and time so severely that there forms a boundary, called the event horizon, beyond which nothing can ever return. Cross that boundary and there is no path back out. Not for a spaceship, not for a beam of light, not for anything at all. Whatever falls in is gone. And because nothing can escape, a black hole seemed like a perfect and eternal trap, a place where things could only accumulate, never leave, growing forever, enduring forever, the one truly permanent structure in a universe where everything else runs down. If anything was going to last to the very end of time, Surely it was the black holes. And then, in the early 1970s, a young physicist named Stephen Hawking discovered something that overturned this picture completely, and it is one of the most beautiful and surprising results in all of modern physics. The more so because Hawking himself was initially reluctant to believe it. Hawking was trying to bring together two great theories that usually live in separate worlds: the theory of gravity, which governs the very large black holes and stars and the shape of space itself, and quantum theory, which governs the very small, the flickering uncertain behaviour of particles and fields. These two theories are famously difficult to reconcile, and much of the deepest frontier of physics lies in the tension between them. But Hawking found a place where they could be made to speak together, right at the edge of a black hole, at the event horizon, and what they said together astonished everyone. To feel the result, you have to know one strange truth about empty space that quantum theory insists upon. Empty space is not truly empty. Even in a perfect vacuum, with all matter and all light removed, the quantum fields that fill the universe are never perfectly still. They flicker and seethe with tiny fluctuations, and in this restless flickering, pairs of particles are constantly, briefly, coming into being and then annihilating one another and vanishing again, so quickly that they are called virtual particles, borrowed momentarily from the energy of the vacuum and paid back almost at once. This is not speculation, by the way. The seething of the vacuum has real, measurable consequences that have been confirmed in the laboratory. Empty space genuinely trembles with this quiet quantum activity, everywhere, all the time, including where you are lying right now. Now, said Hawking, consider what happens when such a flickering pair of particles appears right at the edge of a black hole, right at the event horizon. Ordinarily, the pair would meet again and vanish, borrowing and repaying in an instant, leaving no trace. But at the very edge of a black hole, something new can happen. One member of the pair can fall across the horizon into the black hole, while the other escapes outward, away into space. Now they can never meet again to annihilate. The escaping particle carries real energy away from the black hole, streaming off into the darkness, while its partner falls in carrying, in effect, negative energy that very slightly reduces the black hole's mass. To a distant observer, the black hole appears to be very faintly glowing, radiating a thin trickle of particles and light from just outside its edge. This trickle is called Hawking radiation, and it means that a black hole is not a perfect eternal trap after all. It slowly leaks, it radiates, it loses mass. Given enough time, it evaporates. The rate of this evaporation is astonishingly, almost tenderly slow, and here is a lovely inversion of what you might expect. The larger the black hole, the colder it is and the more slowly it radiates, so that the biggest black holes evaporate the most slowly of all. A black hole with the mass of the Sun would radiate so faintly, so gradually, that it would take something like 10 to the 67 years to fully evaporate. A number with 67 zeros, so far beyond the current age of the universe that the comparison loses all meaning. And the truly enormous black holes, the supermassive ones that sit at the centres of galaxies containing the mass of millions or billions of suns, take vastly longer still, spans reaching to 10 to the 100th power of years and beyond. A 1 followed by 100 zeros, a length of time so immense that every other interval we have discussed tonight, the age of stars, the degenerate era, all of it collapses into a vanishing instant at the beginning by comparison. The black holes are the last great structures standing, reigning over an emptying, darkening universe for spans of time that beggar every word we have for large. But even they, in the end, go. And here is the strangest and most poignant part of the whole process. As a black hole evaporates, it does not fade smoothly to nothing. It shrinks, and as it shrinks, it grows hotter. And as it grows hotter, it radiates faster, so that its evaporation accelerates toward the very end. After spans of time with 100 zeros of patient near invisible leaking, the last of the black hole's mass departs, not with a whimper, but with a final bright flash, a last burst of radiation as the black hole gives up the very last of itself and vanishes completely. Picture it, if you can, across that unthinkable gulf of time, the last black hole in the universe, alone in a dark and nearly empty cosmos, having outlasted every star and every galaxy, and perhaps every atom, finally releasing the last of its energy in a soft final flare, like a long-held breath, at last let go, and then, where it was, nothing. The universe has lost its last great structure, and what remains, after that, is the era toward which everything has been quietly flowing all along, the era we glimpsed at the very start of our walk, the deep and final stillness. So let us go and see what the universe becomes when even the black holes are gone. There is something worth understanding more deeply about why Hawking's discovery was so shocking to physicists, and it connects to that other great law we have carried all night, the law of entropy. Before Hawking, a puzzle had been troubling the people who thought carefully about black holes. If a black hole swallows things and never gives anything back, and if whatever falls in carries entropy with it, then what happens to that entropy? Does it simply vanish from the universe? But the second law says entropy can never decrease, so where does the swallowed disorder go? A young researcher named Jacob Bekenstein had made the daring suggestion that a black hole must itself possess entropy, an amount related to the area of its horizon, so that when it swallows something, its horizon grows just enough to account for the entropy it took in, and the total never decreases. It was a bold and strange idea, and Hawking himself at first doubted it, because if a black hole had entropy then, by the deep connection between entropy and temperature, it would have to have a temperature, and if it had a temperature it would have to radiate, and everyone knew that black holes could not radiate since nothing escapes them. And then Hawking, working through the mathematics that married quantum theory to gravity at the horizon, found to his own surprise that black holes do radiate after all, exactly as a warm object should, and that Bekenstein had been right. The black hole has an entropy and a temperature, and it glows. The two great laws, gravity and thermodynamics, had been quietly reconciled at the edge of the darkest objects in the universe, and the reconciliation predicted their slow eventual death. This is why physicists speak of black hole evaporation with a kind of awe, because it sits at the meeting point of the two theories that are hardest to bring together, and it hints at deeper laws still waiting to be found. And it means that the black holes, which had seemed the one truly eternal thing, the final permanent structures that would surely outlast all else, are themselves only temporary, only very, very slow. They are the longest-lived things we know of, reigning across spans of time with 100 zeros, but they are not forever. Even they are subject in the end to the same law that governs the cooling of your tea, the same climb of entropy, the same slow unwinding. The black holes glow, faintly, coldly, patiently, giving themselves back to the universe photon by photon across ages beyond counting, until at last there is nothing left of them but a final soft flash, and then the dark. And with their passing, the last structures are gone, and the universe has nothing large left in it at all, only the thinning haze and the widening quiet. Let the mind rest a moment against that image before we go further, the last black hole letting go its final breath of light. There is no need to hurry past it. We have come so far now, out past the stars, out past the cooling cinders, out past the slow dissolving of matter itself, and here at the edge of the black hole era we are further from home in time than any thought has any right to travel. And yet the voice telling you this is the same soft voice it always was, and the room you are lying in is the same, and the far future, for all its vastness, cannot reach in and disturb the quiet of this present night. It is only a story, only a shape, only the honest far end of a law you can watch at work in a cooling cup of tea. Breathe, and let us walk on into the last and longest era of all. When the last black hole has evaporated, the universe enters the era that has no natural end, the one that simply continues, the era physicists sometimes call quite plainly the dark era. And to understand what the universe is like then, we have to gather together everything we have learned tonight and follow it to its gentle conclusion. The stars are long gone. The remnants they left have cooled to darkness, or if the proton decays, dissolved entirely into radiation. The black holes have all evaporated, each ending in its soft final flash. What is left is the thinnest imaginable haze, a universe filled with a sparse, cold scattering of the most stable leftover particles, stray electrons and their opposite, the positrons, faint low-energy light, the ghostly neutrinos, all of it spread through a space that has grown, by then, almost incomprehensibly vast. And this is where we must add the other great motion of the universe, the one running quietly beneath everything else we have discussed, because it shapes the final era more than anything. The universe is expanding. Space itself is stretching, has been stretching since the beginning, so that distant galaxies grow ever more distant, not because they are flying through space, but because the space between them is swelling. And this expansion is not slowing down, as astronomers once expected it might. It is speeding up, driven by something we do not understand, a faint pressure woven into empty space itself that physicists call dark energy. We will look harder at dark energy soon, because it holds one of the last great uncertainties of tonight. But for now, simply hold the picture. As the ages pass and the universe empties, it is also swelling ever faster, so that whatever thin scattering of particles remains is pulled ever further apart, diluted across a space growing without limit. Think of what this means for those last stray particles. Picture a single electron drifting alone in the dark era, and its nearest neighbour, another lone particle, so far away across the swelling emptiness that the distance between them is beyond any word we have for far. And that distance grows, and keeps growing, forever. In the earliest universe, everything was packed together in a dense hot brightness, every particle jostling its neighbours. In the final era, every particle is effectively alone, isolated in a darkness so complete and a space so vast that it may never encounter another particle again for the rest of time. The universe has gone from a crowded, blazing, intimate beginning to a scattering of solitary motes drifting in an endless dark, each one alone, the distances between them widening without end. It is the ultimate spreading out, the final and complete triumph of the second law. Entropy climbed as high as it can climb, energy spread as thin and even as it can possibly be spread. This is the heat death, seen at last, not as a fire but as its opposite, a cold so even and so total that there is no longer any difference anywhere between one place and another, no gradient, no flow, no warmth gathered anywhere that could move to anywhere colder, because nowhere is colder, because everywhere is the same. And now think gently of where you are in this story. The atoms in your body, the iron in your blood, the calcium in your bones, the carbon that makes up so much of you, were forged inside stars in the hot cores and violent deaths of suns that lived and died before our own sun was born. You are quite literally made of the ash of ancient fires, gathered up and briefly arranged into something that can lie in the dark and wonder about the end of time. And in the far future, those same atoms, or whatever they become, will still be part of the universe, spread out into the growing dark, mingled into the thin final haze. Nothing is truly lost. It is only spread out, only quieted, only carried outward into the vast gentle evenness of the end. Your matter does not vanish. It disperses, like a lantern's glow softening into a wide darkness, until it is everywhere and nowhere, part of the calm. There is something in this that I find, honestly, more consoling than sad, and I want to offer it to you in that spirit because the same physics that gives us the ending gives us this. Everything that has ever happened, every fire that ever burned, every life that was ever lived, was made possible by the universe's slow unwinding, by the fact that it began wound tight and has been releasing that tension ever since. The starlight that let planets form and warm, the chemistry that let life begin, the energy that powers every thought in your head right now, all of it is the universe spending down its store of order, paying for each bright moment with a little more entropy, a little more of the spring let go. The end we are walking toward is not opposed to the life and light that came before. It is the same process, seen at its finish. The fire and the ash are one thing. And to have been, even briefly, one of the bright arrangements that the great unwinding made possible, to have been a gathered warmth for a little while before the spreading out, is not a tragedy. It is a rare and beautiful thing, and the stillness at the end does not erase it. It only follows it, the way sleep follows a long full day. But I have been speaking of this final era as though it were certain, as though the expansion will simply continue gently forever, and the ending will be this soft, even quiet. And I must be honest with you, as I promised at the start, because there is a genuine uncertainty here, one of the deepest in all of cosmology, and it turns on that mysterious dark energy we set aside a moment ago. Whether the ending is truly this gentle spreading out or something stranger depends on the nature of a thing we do not yet understand. So before we come to rest, we have to look calmly and clearly at what we do not know about the vacuum of space and at the other possible endings that our honest uncertainty leaves open. There is a particular feature of the accelerating expansion that gives the far future a strange and lonely character, and it is worth understanding gently because it changes the shape of the sky long before the truly final eras. Because the expansion is speeding up, distant galaxies are not merely moving away from us but accelerating away, and there comes a point, for each of them, where the space between us and them is stretching so fast that their light can no longer cross the growing gap to reach us at all. One by one, across immense spans of time, the distant galaxies will slip beyond this horizon, their light stretched and dimmed and finally lost until the observable universe, the part we could in principle ever see or reach, contains only our own local cluster of galaxies, bound together tightly enough by gravity to resist the expansion, adrift in a darkness that reaches, uninterrupted in every direction. Any astronomers alive in that far future would look out and see only their own island of stars, with nothing beyond it but black, and they might reasonably conclude that their small cluster was the whole of everything, never guessing at the countless other galaxies that had once filled the sky and had since receded beyond all seeing. There is a quiet melancholy in that thought, that the universe is, in a sense, slowly closing its own book, drawing its distant pages out of reach, so that the full richness of the cosmos is most visible now, in this early bright era, and grows harder to see with every passing age. But I want to hold that not as a loss, but as a reason for a certain gratitude, because it means we are living at a rare and privileged moment in the history of the universe. A moment when the sky is still full, when the light of distant galaxies still reaches us, when the evidence of the whole grand structure of the cosmos is still there to be read. We happen to have arrived while the fire is still bright, while the room is still full of light, while there is still so much to see. Far future minds, if there are any, will have a darker and lonelier sky. We have this one, brimming with stars and galaxies and the ancient light of the beginning, and it will never be quite this full again. To look up now, tonight, at a sky still crowded with light, is to catch the universe in a kind of youth it will slowly and gently leave behind. That is not a sad thought, I think. It is a reason to look up while we can, and to feel lucky for the timing of it, for having opened our eyes in the bright early morning of a very long day. Dark energy is one of the great open mysteries of modern physics, and I want to be very clear about what we know and what we do not, because the whole shape of the ending hangs on it. What we know is this. In the late 1990s, two teams of astronomers, studying distant exploding stars to measure how the expansion of the universe was changing over time, expected to find that the expansion was gradually slowing, gently reined in by the gravity of all the matter pulling inward. Instead, they found the opposite. The expansion is speeding up. Something is pushing space apart, overcoming gravity's inward pull on the larger scales, and driving the galaxies apart at an ever-increasing rate. This discovery was so surprising and so important that it was recognized with a Nobel Prize, and it is now well established that the acceleration is real. That much is settled. What is not settled, not remotely, is what is causing it. We have given the cause a name, dark energy, but the name is really just a label for our ignorance, a placeholder for a thing we can measure the effects of but cannot yet explain. The simplest possibility is that dark energy is a constant, a fixed and unchanging property of empty space itself, a faint uniform pressure that has always been there and always will be, at exactly the same strength everywhere and for all time. If that is what dark energy is, then the future unfolds much as I have described it. The universe keeps expanding ever faster, the galaxies beyond our own local group recede and eventually fade from view entirely, and the long eras play out toward the gentle heat death, the soft even stillness, the quiet spreading out we have been walking toward. This is the mainstream expectation, the picture most cosmologists would offer if pressed, and it is the calmest of the possible endings. But it rests on that assumption that dark energy is truly constant, and we do not actually know that it is. There are other possibilities, and honesty requires that we name them, though we will hold them lightly, as the open questions they are. One possibility is that dark energy is not quite constant, but changes very slowly over time, either weakening or strengthening. If it were to strengthen without limit, growing stronger as the ages pass, it could lead to a dramatically different ending, one that has been given the rather vivid name of the Big Rip. In that scenario, the accelerating expansion would grow so fierce that it would eventually overwhelm not just the forces holding galaxies together, but the forces holding stars, then planets, then atoms, tearing apart every structure in the universe down to the smallest scale in a finale far more abrupt than the slow, gentle fade. I want to be careful here, because this is exactly the kind of thing that gets dressed up in alarm, and there is no need for that. The Big Rip is one possibility among several, not the leading expectation, and even if something like it were the true ending, it lies so unimaginably far in the future that it has no bearing whatever on anything you will ever know or feel. It is simply one of the shapes the honest uncertainty leaves open, and we note it calmly and move on. There is another open question, subtler and stranger, that concerns not dark energy exactly, but the deep stability of empty space itself. Some of our best theories raise the possibility that the vacuum of space, what we think of as the lowest, most stable, most restful state of everything, might not be the true lowest state after all. It might be what physicists call a false vacuum, a state that is stable for enormous spans of time but not perfectly, ultimately stable, rather like a ball resting in a shallow dip partway down a hill, sitting still and quiet for ages but not truly at the bottom. If that were so, then at some point somewhere, the vacuum could settle to its true lowest state, and that change could spread outward. This too is a genuine open question, not an established fact, and the timescales involved are once again so vast as to be beyond any human concern. I raise it not to unsettle you, but because I promised, at the start of tonight, to separate honestly what we know from what we do not. And the truth is that the ultimate fate of the universe rests on questions like these, questions about the deepest nature of empty space, that physicists are still working to answer, and may not answer for a very long time. So here is where we honestly stand, and I think there is a deep peace in standing here clearly. The near future is settled as science gets. The stars will die, the remnants will cool, the black holes will evaporate. About that, the physics is clear and reliable. The ultimate ending, the very last shape of everything, depends on the nature of dark energy and the vacuum, which we do not yet understand, and so several endings remain genuinely possible, a gentle eternal spreading out being the calmest and most favoured, with stranger possibilities held open by our uncertainty. And beneath all of them, in every single version, one thing holds constant, the thing we started with, the one law that only goes forward. Whatever the details, entropy climbs, the universe spreads out and quiets, order gives way to evenness, and time carries everything in the one direction it has always carried it, towards stillness. The uncertainties are real, but they are uncertainties about the shape of the stillness, not about whether stillness comes. And that brings us at last back to the question we set out with, the small light we have carried this whole long way. We have walked to the end, or as near to the end as honest physics can take us. We have seen the fires go out and the embers cool and the black holes fade and the last particles drift apart into an endless even dark. Now, gently, in that final stillness, we can finally ask what it truly means. Because we have been calling this the end of time, but is it? Let us go and look, very softly, at the stillness itself, and at whether the word end was ever the right word at all. I want to add one more layer of honesty here about how we actually measure dark energy, because it grounds all this talk of the ultimate ending in real observation, rather than pure speculation. The way we know the expansion is accelerating comes down, remarkably, to a particular kind of exploding star that serves as a cosmic measuring rod. A certain type of supernova, arising when a white dwarf is pushed past that Chandrasekhar limit we spoke of, explodes with a brightness that is very nearly the same every time, which means that by comparing how bright such an explosion appears to us with how bright we know it truly is, we can measure exactly how far away it lies. These are the standard candles of cosmology, reliable lights of known strength scattered across the depths of space. By finding such explosions at many different distances, and measuring both how far away they are and how fast the space around them is receding, astronomers could trace the history of the expansion itself, could see how the rate of stretching had changed over billions of years. And what they found, against all expectation, was that the expansion had been slowing in the ancient past as gravity worked to rein it in, but had then begun, some billions of years ago, to speed up again, as though some faint persistent pressure had gained the upper hand over gravity as the matter thinned out. That turning point from slowing to speeding is the fingerprint of dark energy, and it is written in the light of these exploding stars and it has been checked and rechecked by independent methods, and it holds. The acceleration is real. It is only its cause, its deep nature, whether it is truly constant or slowly changing, that remains genuinely unknown. And so we are left in a position that is, when you look at it rightly, rather wonderful. We can measure with real precision a thing we cannot explain. We can chart the acceleration, weigh its effect, follow its consequences out into the far future, and yet we cannot say what it fundamentally is. This is not a failure. It is the living edge of science, the place where careful measurement has run ahead of understanding, where we know that something is there and know a great deal about how it behaves without yet knowing what it truly is. Physics is full of such moments, and they are not to be feared. They are invitations. Each one is a door still open, a question still breathing, a piece of the world still waiting to be understood. And the final fate of the universe, the very last shape of everything, hangs on one of these open doors, which means that the ending of the story is, in the most literal sense, not yet written. Not because the universe is undecided, but because we have not yet learned enough to read the last page. There is something I find deeply restful in that. The book is not closed. Even the end is still, in part, a mystery, and mystery, gently held, is one of the most soothing things there is. Come and stand with me then, in the final stillness, and let us simply look at it, slowly, without hurry, because this is the place the whole walk has been leading toward, and it deserves to be seen clearly and gently. Imagine the universe in that last dark era, space stretched almost beyond meaning, the last light so faint and so spread out that there is no brightness anywhere, only the dimmest possible glow softening imperceptibly toward nothing. The last particles so far apart that each drifts utterly alone, with no neighbour near enough to touch or pull or ever meet. No stars, no galaxies, no black holes, no fires of any kind. Only a vast, cold, even silent expanse, growing slowly ever vaster, in which almost nothing ever happens, and then, as the ages deepen beyond all the ages, less and less, until it seems that nothing happens at all. Picture a pond at the very end of a still evening, after the last ripple has crossed it and faded, after the last leaf has settled and gone quiet, when the surface has become so perfectly smooth and so perfectly still that it is more like a held idea of water than water itself, a stillness so complete that time seems to have set it aside. The final universe is like that pond, but larger than every largeness and stiller than every stillness. A smoothness, with no ripple anywhere and no source of any ripple left, every motion spent, every difference erased, everything that could happen having already happened unimaginably long ago. And here, in this perfect stillness, we come to the quiet turn that the whole night has been carrying toward, the thing I promised at the beginning without saying what it was. It is this: in a universe where nothing changes, where there is no motion and no event and no difference between one moment and the next, what would it even mean for time to pass? Think about how you actually know that time is passing, right now, tonight. You know it because things change, the clock hand moves, your breath goes in and out, the candle burns lower, a thought gives way to the next thought. Time, as we experience it, and as physics measures it, is bound up entirely with change, with events, with one thing following another. Every clock that has ever been built, from a swinging pendulum to the trembling of an atom, tells time by counting changes, by marking one state giving way to the next. Time is measured in differences, and in the final stillness, when every difference has been spread away and nothing changes anymore, there is nothing left for any clock to count. There are no events to mark. There is no next state that differs from this one. And so, in a strange and gentle sense, time itself has nothing left to measure, nothing left to be made of. This is what I meant at the very start when I said the wall you were expecting might not be there. We set out asking whether time could end, picturing a final moment, a last tick, a hard edge beyond which there is nothing. And what the physics actually gives us is stranger and softer than that. It gives us not a wall but a fading, not a stop but a stilling, not a final moment but the quiet dissolving of the very thing, change, that moments are made from. Time does not slam shut. It runs out of things to do. The universe does not end at a boundary. It settles so completely and so evenly, that the difference between one time and another simply ceases to mean anything, the way the difference between one part of that perfectly still pond and another ceases to mean anything once every ripple is gone. There is no last tick of the clock because in the end there is nothing left for the clock to tick against. The end of time, if we must call it that, is not an event. It is the absence of events. It is not a moment. It is the quiet after the last moment, stretched out into a stillness that no longer needs the word after at all. And notice, this is a far gentler thing than the wall we feared. A wall is violent, abrupt, a slamming shut. What physics actually describes is more like the way a piece of music ends, not with the sound being cut off, but with the last note allowed to ring and fade and soften until you cannot say exactly when the silence began, only that at some point the room is quiet and has been quiet for a while, and the quiet was always where the music was going. The universe does not get switched off. It relaxes, it exhales, it comes, across spans of time beyond every number, to rest. And rest, of all the words we have used tonight, may be the truest one for what waits at the end. Not death, not doom, not a wall, but rest, the deepest and most complete rest there could ever be, the stillness that every ripple was always quietly heading toward from the very first. So the word end, which we carried so carefully all this way, turns gently in the hand and shows another face. What ends is not existence exactly, and not even quite time exactly. What ends is change and difference and event, and what remains is a stillness so total that the question of whether time is still passing loses its grip, because there is nothing left for the passing to mean. It is less an ending than an arriving, less a stop than a settling, less a wall than a horizon that recedes as you approach it, so that you never quite reach a final edge, only an ever-deepening calm. And having seen that, having walked all the way out here to the still pond at the end of everything and looked at it plainly, we can turn now and gather up what we have learned and let ourselves come, softly, to rest. Let me hold the image of that final stillness a little longer and turn it once more, because there is a subtlety in it that rewards a slow and gentle look. We tend to think of time as a river, flowing steadily along whether or not anything floats upon it, a current that would keep running even through a perfectly empty channel. But some of the deepest thinking in physics suggests that this picture may be exactly backward, that time is not a river that would flow through emptiness, but something more like the counting of changes, meaningful only where there are changes to count. A clock does not measure some abstract flow. A clock is a thing that changes in a regular way, a pendulum that swings, an atom that vibrates, and it measures time by counting its own changes. Take away all change, everywhere, and you have taken away not just the clocks but the very thing the clocks were counting. In the perfect final stillness, there is no swing and no vibration and no event, and so there is, in a real sense, nothing for time to be the measure of. Time does not stop exactly, the way a film stops on a frozen frame, because even a frozen frame is a moment held in a longer sequence. It is subtler than that. Time simply ceases to have anything to distinguish one moment from the next, and where nothing distinguishes them, the very idea of one moment following another loses its foothold. This is why the word end sits so awkwardly on what actually waits out there. An end is an event, a happening, a last thing that occurs, but the stillness is precisely the absence of events, and so it cannot really contain a final one. There is no last tick, because a last tick would itself be a change, and change is exactly what has been spread away. What waits is not a final event, but the quiet closing of the very possibility of events, which is a stranger and softer thing than any ending we could picture. It is less like the last page of a book and more like the way a book set down and unopened simply rests, its story neither ended nor continuing, only held, complete and still, in the quiet. The universe does not reach a last moment and stop. It relaxes so completely that the difference between moments fades, and with it fades the meaning of the question we started with. We asked whether time could end, and the honest, gentle answer the physics gives is that time does not so much end as grow still, and that stillness, deep enough, is a thing our ordinary words were never quite built to hold. Let us gather it gently then, everything we have carried tonight, and hold it all together one last time before we let it go soft. We began with a single law, the one rule in physics that only ever runs one way, entropy always climbing, the great spring of the universe slowly unwinding, and we saw that this one law is the source of time's whole direction, the reason the cup shatters and never mends, the reason you remember the past and lean toward the future. We met the people who found it, the young engineer thinking about steam engines, the careful physicist who gave disorder its name, the melancholy genius who saw that it was all in the end a matter of counting the countless ways that things can be. And then we followed that law outward, out past the death of our own sun in its 5 billion years, out past the last of the patient red embers 100 trillion years from now, out through the long, cold twilight of the stellar remnants, past the slow, possible dissolving of matter itself, out across the almost endless rain of the black holes and their soft final flares, and out at last into the deep, still dark where the last lonely particles drift forever apart. And I want, before we rest, to set down clearly what we truly know and what we do not, because that honesty is the quiet gift of a night like this. What we know, as surely as we know anything, is the near shape of the future. The stars will burn out, each in its own time. The remnants they leave will cool. The black holes will evaporate however long it takes. Entropy will climb, and the universe will spread out and quiet down, and time will carry everything in the one direction it has always gone. That much is settled, tested, reliable. What we do not know is the very last shape of it all, because that depends on things we have not yet understood. The true nature of dark energy, the deep stability of empty space, questions at the living frontier of physics that may not be answered for a long time yet. The gentlest ending, the slow, even spreading into stillness, is the one most physicists would name as likeliest. But the honest truth is that several endings remain open, and we hold them lightly without fear, as the open questions they genuinely are. And there is one thing further out still, past even those open questions, that may simply be unknowable, may lie forever beyond the reach of any instrument or any mind, and that too we can set down gently, because there is no burden in admitting that some things are beyond us. It is restful even to lay it down. But here is what I most want to leave with you as the light goes soft. The end we walk toward tonight is not a doom, and it was never a doom. It is a settling. It is the same quiet process you can watch in a cooling cup of tea, only carried out to the scale of everything and the fullness of all time. And every bright thing that has ever been, every star, every world, every living warmth, every thought you have ever had, was made possible by exactly this process, by the universe spending its long store of order to buy, for a little while, the fires and the light and the gathered warmth of things like us. The ending does not cancel the beginning. The ash does not erase the fire. They are one thing seen at its two ends. And to have been, even for the briefest flicker, one of the bright gathered warmths that the great unwinding allowed, is not a small thing and not a sad thing. It is a rare and lovely thing, and the long stillness that follows does not take it away. It only follows it, the way rest follows a full day, the way quiet follows the last soft note. So let the far future be what it is, out there beyond every number, and let it be gentle, because it is. You do not have to hold any of it. You do not have to carry the stars or the black holes or the cold last dark out of this room with you. They will keep, out there in the deep time where they belong, and they ask nothing of you tonight. All you have to do now is rest here, in the warm near present, in this small bright gathered moment that the whole unwinding universe made room for, this night, this breath, this quiet. And far, far ahead, past everything, there is that last dim red light we began with, the final ember in the dark, growing softer and softer, warmer than the cold around it by the gentlest margin, fading so slowly that you could never say the moment it was gone. Let your eyes rest on it, that small warm point at the very end of time, and let it grow dimmer and dimmer still and softer, until it is less a light than the memory of a light, less a glow than the deep calm where a glow once was. There is nothing to wait for now. There is nothing you need to do. There is only the soft red fading and the widening quiet and the stillness settling over everything, gentle and complete, like the last warmth of a fire in a room where someone has finally, peacefully, fallen asleep. There is one more thing I want to give you before the light goes fully soft, a thought to carry down into sleep, and it is about the strange good fortune of being here at all, now, in this particular chapter of the universe's long life. Of all the eras we have walked through tonight, the bright age of stars is by far the briefest. It is the thin opening slice of a story that runs on, dark and still, for spans beside which the whole age of starlight is a single flash. And yet it is only in this brief bright slice that anything like us could ever exist. Only here, where there is still starlight to warm worlds and forge the elements of life and light the sky, that a creature could arise capable of looking out and asking how the story ends. The long dark eras that follow are vast, almost beyond reckoning, but there is no one in them to know it, no eye to see the last black hole fade, no mind to feel the final stillness settle. All the knowing, all the wondering, all the love and curiosity and quiet awe that the universe has ever contained or ever will, is crowded into this narrow bright morning, this early flicker before the long night. We are not living at the end of things, we are living at the beginning, in the rare warm window when the lights are still on and someone is here to notice them. And so, the far future, for all its immensity, is not something to carry as a weight. It is something that makes the present more precious, not less. The stillness at the end does not reach back to touch this night. It does not dim the light in your room, or cool the warmth of your own breathing, or lessen, by even a little, the simple fact that you are here now, in the bright early age of the universe, alive and aware and gently drifting towards sleep. The end is real, and it is gentle, and it is unimaginably far away, and between here and there lies everything, all of it still to come, all of it still bright. You do not need to hold any of the darkness. You only need to rest here, in the light, while the light still shines, which is now, which is tonight, which is this very breath you are taking as your eyes grow heavy,